Welcome back to the lecture hall, everyone. I am absolutely thrilled to have you here for today's explainer. Today, we're adopting the mindset of a university geologist to explore something truly fascinating: the hidden, immense physical forces that shape the solid rock right beneath our feet. You know, we often think of the ground as static and unyielding, right? But the reality is that the Earth's crust is a highly dynamic environment, and it is governed by strict mathematical and physical laws. Today, we are going to unpack exactly what those laws are.
Here's our syllabus for today's masterclass. 1. The primer. 2. Types of rock stress. 3. The 3D stress cube. 4. Principal stress axes. 5. The math of stress. And finally, 6. Drawing the Morse circle. Let's build this step by step.
Section 1. The primer. Stress versus pressure. Before we crunch any numbers, we absolutely have to get our definitions crystal clear.
In basic physics, force is just mass times acceleration. But stress? Stress is a bit more complex. It involves a pair of equal and opposite forces acting on a specific planar portion of a body. And because of Newton's third law, these forces actually cancel each other out. So we define stress as the amount of force per unit area, typically measured in newtons per square meter, or pascals. And since we're dealing with forces distributed over an area, stress is actually a tensor, not a simple vector, with dimensions of mass over length times time squared.
Now, here's a trap I see people fall into all the time: confusing stress with pressure. They are definitely not the same thing. Pressure, like hydrostatic pressure deep down in the ocean, acts equally from all sides. It's ambient. Stress, on the other hand, is highly directional. It acts on very specific internal planes within a solid body.
Think about a heavy book resting on a table. It exerts a generalized downward pressure. But deeper inside a block of solid rock, directional forces are reacting along a very specific inner plane within the solid material. Essentially, the rock is pushing back against itself.
Section 2. Types of rock stress. Let's see what happens to the rock when we change the orientation of those internal forces.
Depending on their relative orientations, stresses are classified into 3 main types. First, we have compressive stress, where the forces act towards each other, literally squeezing the rock and shortening its length. Second is tensile stress, where the forces pull away from each other, stretching the material. And third, we have shear stress, where the forces act in opposite, parallel directions. These directional stresses physically deform the rock, changing its lengths and angles, and that resulting physical change is what we refer to as strain.
Section 3. The 3D stress cube. Okay, let's take our 2D calculations and drop them into a complete 3D Cartesian space so we can understand true subterranean rock mechanics.
Imagine a vertical compressive force pushing straight down on a block of rock, but hidden inside that rock is a pre-existing inclined plane, like an old fault line. That oblique force doesn't just push straight down on the plane. Because stress is a tensor, we can resolve that vertical force into 2 distinct components relative to the plane's surface: a normal stress, which acts perfectly perpendicular to the surface, and a shear stress, which acts parallel to it, trying to slide along the surface.
Now, if we zoom way in on a single point in space and visualize it as an infinitesimally small cube, we can fully describe the stress acting on it. Each face of this cube experiences 1 normal force and 2 perpendicular shear forces. Across the 3 visible faces, that produces 9 stress components in total, 3 normal and 6 shear. But don't worry, the opposing shear forces are perfectly equal. If they weren't, this little cube would rapidly spin out of control. They completely balance out, preventing any rotation.
Section 4. Principal stress axes. 9 components is a lot of math, so we need to find a way to simplify this chaotic 3D stress field into something we can actually work with.
So here is the trick. What if we conceptually rotate our tiny cube? If we turn it just right, orienting its faces perfectly within the stress field, the shear forces parallel to the surfaces actually drop to absolute 0. When shear is 0, the stress on the cube is described entirely by 3 simple normal force factors. We call these the principal stress axes. We label them sigma 1 for maximum stress, sigma 2 for intermediate, and sigma 3 for minimum stress. By finding these axes, we've basically organized the chaos.
Section 5. The math of stress. Grab your virtual notepads because we are going to look at the exact mathematical formulas used to calculate these forces on any given inclined plane.
Before I throw a bunch of complex calculus your way, nature actually gives us a massive shortcut. At shallow depths in the Earth's crust, the main cause of stress is simply the crushing weight of gravity from the rocks above. This creates a massive vertical compressive stress, our maximum stress, or sigma 1. The horizontal stresses in this scenario are usually equal to each other. Because of this, we can safely ditch the 3D headache and approach our calculations from a purely two-dimensional perspective, focusing exclusively on the maximum stress sigma 1 and the minimum stress sigma 3.
If we have a fault plane cutting through the rock at a specific angle, let's call it theta, we can calculate the exact normal stress pressing perpendicular to that plane. The formula is the normal stress equals 1/2 of sigma 1 plus sigma 3, added to 1/2 of sigma 1 minus sigma 3, multiplied by the cosine of 2 theta. It looks like a mouthful, but it simply means the crushing force on the fault plane changes smoothly depending on its angle. This is exactly how geologists predict if a fault line is going to slip and trigger an earthquake.
And for the shear stress, the force actively trying to slide the rock along that fault plane, the equation is 1/2 of sigma 1 minus sigma 3, multiplied by the sine of 2 theta. Now look closely at the hidden geometric truth in this equation. Because it relies on the sine of 2 theta, the maximum possible shear stress will always occur when 2 theta equals 90 degrees. That means the plane of absolute maximum shear stress within a rock will always sit precisely at a 45-degree angle to the primary vertical stress sigma 1. It's just a beautiful mathematical certainty built directly into the crust of the Earth.
Section 6. Drawing the Moore circle. While the algebra we just covered is incredibly important, field geologists really don't want to run trigonometric functions on a calculator all day. There's a far more elegant visual way to find these values.
Enter the Moore circle. This is a brilliantly simple graphical representation invented over a century ago. It completely bypasses the complex trig equations we just went over, allowing us to map out the shear and normal stress acting on any inclined plane simply by drawing a circle on a graph.
Here's how you construct it step by step. First, you draw your standard orthogonal axes. The horizontal axis is our normal stress, and the vertical axis is our shear stress. By convention, we place compressive stresses on the positive side of that horizontal axis. Next, you plot your minimum and maximum principal stresses, sigma 3 and sigma 1, on the horizontal line. Finally, you find the exact midpoint between those two plots. That midpoint becomes the center of your circle, and the distance between sigma 1 and sigma 3 becomes the diameter. Draw your circle and boom, your graph is set.
And here is the absolute magic of this graphical method. Once your circle is drawn, you can find the stress forces on any fault plane instantly. Just draw a straight line starting from the sigma 3 point at your physical fault angle, theta. Or, alternatively, draw it from the center of the circle at double the angle, 2 theta. Where that line intercepts the circumference of your circle, you just read the coordinates. The horizontal coordinate gives you the exact normal stress, and the vertical coordinate gives you the exact shear stress. No calculators required. It's a perfect geometric mirror of the physics happening miles underground.
It really makes you think, doesn't it? If something as elegantly simple as the Moore circle can take the chaotic, crushing 3D forces of subterranean geology and translate them into a perfectly readable 2D diagram, what other immense, invisible forces in nature are just waiting for the right visual key to decode them? Keep that question in mind the next time you look at a complex physical system. Thank you so much for joining me for this explainer today. Keep learning, keep questioning, and I'll see you in the next one.